Hello students, I am Dr. Shilpa K. Gowda, Associate Professor, Department of ECE, SJBIT. Today I am going to explain the topics related to basic electronics. So first, we will start with the module 1, semiconductor diode and its applications. So these are the topics related to first module, that is semiconductor diodes, diode applications and Zener diodes. So first we will start with the semiconductor diodes. So first in that we will consider the introduction. So we know that based on electrical properties, materials can be classified as conductors, insulators and semiconductors. These allow, like if conductors means they allow electric current to pass through it. Insulators means they do not allow electric current to pass through it. Semiconductors means electric conductivity is between a conductor and insulator. As far as the electronic components are concerned, semiconductors are the most important type of materials. The most widely used semiconductor materials are silicon and germanium. Semiconductors are classified as intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors. In intrinsic semiconductors means it is pure. That means that intrinsic semiconductors are the semiconductors in their purest form. That means that the presence of impurity is very low. Extrinsic semiconductors. In extrinsic semiconductors means so it means that it is an impure. So we can obtain the extrinsic semiconductors from intrinsic ones by adding the impurities to it. The process of adding impurities is called doping. Due to doping, the conductivity of the semiconductor increases. Thus, extrinsic semiconductors have a better conductivity than the intrinsic semiconductors. Therefore, they are used in manufacturing of all the electronic components such as diodes, transistors, etc. Next, we have extrinsic semiconductors. So, these extrinsic semiconductors can be classified as P-type semiconductor and N-type semiconductor. In P-type semiconductors are obtained by adding a trivalent impurities like aluminium, boron, etc. And in a p-type semiconductor, hole is the majority carrier and electron is the minority carrier. Next we have n-type semiconductor. In n-type semiconductors are obtained by adding pentavalent impurities like arsenic, phosphorus, etc. And in a n-type semiconductor material, electron is the major carriers and hole is the minority carrier. So next we have PN junction. So that means that how to form a PN junction. A p-type semiconductor and n-type semiconductors are combined together with a special fabrication technique to form a PN junction. The N side consists of a large number of electrons and a few thermally generated holes, whereas the p-type semiconductor consists of a large number of holes and a few thermally generated electrons. Thus, the electrons are majority carriers and holes are minority carriers in N region, whereas their holes are exactly opposite in the P region. The PN junction forms the basic semiconductor device called diode. After the formation of PN junction, when no external voltage is applied, then the free electrons from N side will diffuse into the P side and recombine with the holes present there. Each electron diffusing into the P side will leave behind a positive immobile ion on the N side. When an electron combines with a hole on the p side, an atom which accepts the electron loses its electrically neutral status and becomes a negative immobile ion. Due to this recombination process, a large number of positive ions accumulate near the junction on the N side and a large number of negative immobile ions will accumulate on the p side near the junction. The negatively charged ions on the p side will start repelling the electrons which accept to diffuse into the p side, and after some time the diffusion will stop completely. At this point the junction is said to have attained an equilibrium. The p-n junction in the state of equilibrium. The shaded region on both sides of the junction contains only immobile ions and no free charge carriers such as electrons or holes. In other words, this region is depleted of the free charge carriers. Therefore, this region is called as the depletion region. This region is also known as the space charge region. In the state of equilibrium, the depletion region gets widened to such an extent that electrons cannot cross the junction anymore. The width of depletion region is extremely smaller. Practically, it is of the order of zero point 0.5 to 1 micron, where 1 micron corresponds to 1 into 10 power minus 6 meters. Due to the presence of immobile positive and negative ions on opposite sides of the junction, an electric field is created across the junction. This electric field is known as the barrier potential or junction potential, or also it is called as a cut-in voltage, and it has a fixed polarities. The barrier potential or cut-in voltage for silicon is 0.6 volts, whereas its value for the germanium is 0.2 volts. Next, we have PN junction diode. This is a PN junction diode, where the PN junction which forms the semiconductor device called a semiconductor diode. The meaning of the term diode is the device having two electrodes. The diode has two electrodes, one on each for the two regions on either sides of the junction. The two electrodes are named as node and cathode. That is, it has name as anode and cathode. The arrow head in the symbol points in the direction of a convention current through the device. This current will flow through the diode if and only if an external voltage source is connected to it with appropriate polarities. Next, we have characteristics. So that is the characteristics of a diode. That is VI characteristics of a diode. So to plot a graph of a VI characteristics of a diode, first we have to analyze depending. We have to analyze the diode depending upon the biasing conditions. Biasing is the process of applying an external DC voltage to the semiconductor diode. When the external voltage is not applied to the diode, the BN junction continues to be in the state of equilibrium. Therefore, there is no current flowing through it. To make the current to flow, it is necessary to bias the diode. The biasing can be of two types. The one is forward bias and second one is reverse bias. So first we'll consider forward biasing of a diode. If the P region, that is anode, is connected to the positive terminal of the external DC source and N side is connected to the negative terminal of the DC source, then the biasing is said to be forward biasing. In other words, the diode is then said to be forward biased. Generally, a resistance is connected in series with the diode to limit the current flowing through it. The current I is a conventional current that flows in the circuit due to forward biasing. Due to the negative terminal of the external source connected to the N region, free electrons from N side are pushed towards the P side. Similarly, the positive end of the supply will push holes from P side towards the N side. The external DC voltage opposes the barrier potential or junction potential and reduces it from Vj to minus V minus Vj. As the barrier potential decreases, the electrons and holes can penetrate the depletion region. As we increase V, the barrier potential Vj keeps reducing. At a certain voltage V will overcome the barrier potential and the current will flow begin. With increase in forward voltage, the barrier potential will reduce the width of the depletion region and eventually the depletion region will collapse. When the depletion region collapses, a large number of majority carriers can cross the junction under the influence of the externally connected DC voltage. The large number of majority carriers crossing the junction constitute a current called as the forward current. The current flow is the electron which is in the opposite direction to that of a conventional current. The forward current to a PN junction diode flows due to the majority carriers. Next, we have a characteristics of an idealized VI diode, that is forward characteristics of a diode as well as a reverse characteristics of a diode. That's for the behavior, that is first we'll consider forward characteristics of a diode. The behavior of a PN junction diode is indicated by the volt ampere characteristic, that is VI characteristics. The VI characteristics of a PN junction diode is a graph of voltage across the diode versus the current flowing through it. If a diode is forward biased, then the voltage across it is denoted by Vf and forward current is If. The VI characteristics is that is the forward characteristics is divided into two portions A, B, B, C. That is, in the region A to B of the forward characteristics, the forward voltage is small and less than the barrier potential. Therefore, the forward current flowing through the diode is small. With further increase in the forward voltage, it reaches the level of barrier potential and the width of depletion region goes on decreasing. As soon as the forward voltage equals the barrier potential, current through the diode increases suddenly. The nature of this current is exponential. The large current in the region B to C of the forward characteristics is limited by connecting a resistor R in series with the diode. The forward current is the order of a few milliamps. And also the forward current is a conventional current that flows from anode to cathode. Therefore, it is considered to be a positive current and the forward characteristics appears in the first quadrant as shown in the figure. The voltage at which the forward diode current starts increasing rapidly is known as the cut-in voltage of a diode, and the cut-in voltage is very close to the barrier potential and it is denoted by V alpha. Next, we have reverse bias of a diode. That is, in the reverse bias, if the P region of a diode is connected to the negative terminal of the external DC supply and N region is connected to the positive terminal of the DC supply, then the diode is said to be reverse bias. So next we'll how the reverse bias will operate. When a diode is reverse biased, holes in the P region are attracted towards the negative terminal of the supply and electrons on the N side are attracted towards the positive terminal of the supply. Due to movement of electrons and holes away from the junction, width of the depletion region increases as shown in the figure. This happens due to the creation of a more number of positive and negative immobile ions. Due to more number of ions present on opposite sides of the junction, the barrier potential or junction potential will increase. That is, the process of widening of a depletion region does not continue for a long time because there is no steady flow of holes from right to left, that is from N side to P side. The that is the reverse characteristics is a graph of a reverse voltage versus the reverse current as shown in the above figure. Current flowing through a diode in the reverse bias state is the reverse saturation current, which flows due to the minority carriers. Therefore, it is treated as a negative current. Hence, the reverse characteristics appear in the third quadrant as shown in the above figure. Next, we will start with the main parameters of the diode. The main parameters of the diode is are the ratings of diodes, which is important in circuit design and component selection. Some of the widely used diode specifications are new voltage or forward voltage or cut-in voltage. That is, it is the voltage applied across a forward bias device, or the forward voltage is the voltage at which the current through the junction starts to increase rapidly. The new voltage or cut-in voltage for silicon is 0.7 volts and for germanium is zero point 0.3 volts. Next, we have reverse breakdown voltage. It is the minimum reverse voltage at which PN junction breaks down with the sudden rise in reverse current. That is, VBR is around 50 volts for germanium diode and 75 volts for silicon diode. Next, we have peak inverse voltage. It is the maximum reverse voltage that the diode can withstand without destroying the junction. Next, we have forward current. It is a current flowing through forward biased diode measured in milliampere. Next we have reverse current. It is a current flowing through reverse biased diode. Next, power dissipation. The power dissipation in a diode for a given value of diode voltage and current. Next, dynamic resistance. It is the resistance offered by a diode under changing levels of the forward voltage. Next, we have the characteristics and parameters. So, this is the typical forward and reverse characteristics of a silicon diode. So next, ideal. These are the ideal factors of a diode. That is, the parameters of the greatest are forward voltage drop, reverse saturation current, reverse breakdown voltage, dynamic resistance, and maximum forward current. So next, we had this is the determination of diode dynamic resistance from the forward characteristics. Next, this is the diode approximation. So diode is approximation is nothing but a diode equivalent circuit. An equivalent circuit for a device is a circuit that represents the device behavior under forward and reverse bias conditions. So first one, ideal diode equivalent circuit. The diode conducts when it is forward bias and has a zero resistance. The diode blocks the conduction when it is reverse bias and has an infinite resistance, and it acts as an open switch. Next, second one is a practical diode equivalent circuit. So the diode equivalent circuit consists of a voltage source and negligible forward resistance. This equivalent circuit has the second approximation characteristics. Next, we have third approximation or piecewise linear or a complete DC circuit. The equivalent circuit consists of a diode dynamic resistance in series with the voltage source, and an ideal diode is included to show that the current flow only in one direction. Next, this is the linear characteristics of the diode forward characteristics. This is next step we have DC load line analysis. That is the graphical analysis used to calculate the precise value of diodes voltages and current is called a DC load line analysis. So first we'll consider the simple diode circuit where diode is forward bias and the forward current flows through resistor R, which is shown in the figure there. Applying KVL rule there, we will get that V equals VF and IF equals V by R. Joining the lines, then we can joining the lines A, B to get a DC load line. So then we will get it here IF equals minus 1 by R into VF plus V by R, which represents this straight line equation Y equals MX plus C. The intersection of the diode forward characteristics and the DC load line is called Q set point or operating point.